just obtained by purifying bauxite. Right. Alumina is very important in extraction of aluminium, and in these videos you should be able to perform the following activities after the video. You should be able to describe why electrolysis is used to extract some metals like aluminium, for example. You should be able to describe how aluminium is extracted by electrolysis, and you should be able to write equations, half equations and the overall equation for the extraction of aluminium. Now, when you want to extract aluminium by electrolysis, why do we do that? Why do we need to extract aluminium by electrolysis? Why not by chemical reduction? Why not by using carbon? Now, the reason we are going to extract aluminium by electrolysis is because aluminium is an highly reactive metal. You extract reactive metals by electrolysis because they are more reactive than carbon, so you cannot reduce them with carbon. So you only left with electrolytic reduction. And apart from aluminium, you will observe that sodium, potassium, calcium, magnesium are also extracted by aluminium. Something is very common to those elements. Their name ends with ium, 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 ium. So you can safely conclude that elements among the first 20 whose names ends with ium are extracted by electrolysis. It's okay. It's just a shortcut, and it might help you in objective questions. So let's move on. When you want to extract aluminium by electrolysis, the electrolyte that you use is alumina. That is why it is very important for us to purify our bauxite first before we start extracting aluminium. So you use alumina, pure alumina, as the electrolyte. But this pure alumina is always dissolved in molten cryolite. You can see cryolite, molten cryolite. Now, molten cryolite is used to dissolve alumina, and the solution is used as electrolyte when we're extracting aluminium. The question is, why do we use molten cryolite? What's the purpose of molten cryolite in extracting aluminium? We use molten cryolite to reduce the melting point of aluminium oxide. It is very expensive to keep aluminium oxide molten because the melting point is above 2000 degrees Celsius, around 2019 thereabout degrees Celsius. So, but when you add molten cryolite to serve as impurity, you remember that impurity reduces the melting point. So when you add molten cryolite to act as impurity, it's going to reduce the melting point of alumina to around 950 degrees Celsius. So that is the number one reason, importance of using molten cryolite to dissolve alumina, to keep the melting point low, to lower the melting point. Then number two is to increase the conductivity of alumina. Then number three is it acts as a solvent for alumina. Those are the three reasons why you are going to add cryolite when you are electrolyzing aluminium oxide. The process by which we extract aluminium from alumina is called Hall Heroult process. Hall Heroult process. It's that Hall Heroult is the name of a man that discovered how to electrolyze how to prepare aluminium by electrolysis. Hall Heroult process. The Hall Heroult process uses a reduction cell. This reduction cell to electrolyze alumina. If you open the cell, you are going to see something like this inside. When the cell is opened, you observe that we have the anode and the cathode. You see the anode. Whenever you see this kind of wire joined to an electric supply, is an electrode. We also have another electrode in this place. So two electrodes like that connected to a power supply, you should know that an electrolytic cell. Now, this cell is made of a steel container. This brown substance is a steel container, while the inside is lined with graphite. This lining of the container, the inside lining, is graphite. So the container essentially contains graphite lining inside the steel container. So that graphite lining serves as a cathode. That graphite lining serves as a cathode. You can see the carbon lining is the cathode in this place. So this is the cathode in this place. The lining of the container is the cathode. Why these three blocks of carbon are the anode? So this serves as the anode, while the lining serves as the cathode. Don't forget, then this is the electrolyte inside the reduction cell. The alumina is the electrolyte already dissolving cryolite. The cryolite will lower the melting point. Don't forget that. Now, when you connect this to a power supply, you are going to observe something happening to the aluminium oxide. Observe this aluminium oxide join together. When you connect them to a power supply, the aluminium will split from the oxygen. You can see this already. The aluminium is already splitted from the oxygen. You can see aluminium already splitted going to the cathode. The cathode is the lining, so they will move to the cathode. While the oxide ion, the oxygen, is an anion, so it moves to the anode. Anion goes to the anode, while cation goes to the cathode. Remember that. Okay, so that is what happens when you connect them to an external supply. So at the anode, the oxide ion will lose 2 electrons and be released as oxygen gas, while the aluminium ion will get to the lining, which is the cathode, collect 2 electrons and then become aluminium metal. So you are going to observe that the aluminium metal that is formed will flow out of this tap into this container. So that is how we prepare aluminium by Hall Heroult process. So this aluminium coming out from the tap into this container. So what are the reactions at the cathode? At the cathode, we said that aluminium ion will gain electrons. That is, it has gained 3 electrons already. So when it gains the 3 electrons, it's going to become aluminium metal. As you can see, that's a reduction reaction. Gain of electron is reduction, represented by Rig. Rig means reduction is gain. So at the anode, the oxide will lose 2 electrons. You can see at the anode, the oxide will lose 2 electrons and turn to oxygen. But remember that the oxygen is diatomic, so we need 2 atoms of oxygen to form an oxygen gas. So what will happen is this. So eventually the 2 oxygen will be losing 4 electrons overall. So this is what will happen at the anode. 2 oxide ion become oxygen gas, losing 4 electrons. But something else also happens at the anode, which I want you to take note of. At this anode, when oxygen gas is given off, the temperature of that reaction is very high, such that oxygen can react with the carbon blocks, the carbon that is serving as the anode. Oxygen can react with it at that temperature of 950 degrees Celsius. So all these oxygen that have been used as the anode will gradually react with all this oxygen that is being evolved at the anode will gradually react with the carbon anode itself, these blocks of carbon will react with the oxygen to form carbon dioxide. So you are going to observe that these blocks of carbon will be depleting, that is, will be reducing in size because it is forming carbon dioxide gas whenever the oxygen is being released at that particular place. So you are going to see that at regular interval, carbon anode needs to be replaced because it is continually reacting with oxygen that is produced at the anode to form carbon dioxide gas. So it's an examinable question that why do we need to replace the carbon anode at regular interval? It's because at that temperature, at high temperature, carbon anode will react with the oxygen that is being produced at the anode and get depleted as carbon dioxide gas. So that is why we are going to need to continue to replace the anode. So the reaction that occurs there is very simple, and this is the reaction that occurs in that place. Carbon anode, which is the C here, will react with oxygen that is formed at the anode to produce carbon dioxide gas. So that is why the carbon anode will be depleting at regular interval and will be depleting continuously and must be replaced at regular interval. In the industry, you do this every 28 days. So that is what happens at the anode. Now let's see the overall reaction of the electrolysis. We have already seen that the aluminum ion is reduced at the cathode, while the other ion is oxidized at the anode. Now we know that for us to write an overall equation, this electron must be equal before we can cancel out the electron and merge the two equations. Now for the electron to be equal, what can we do? What can we do to make the electron equal? Multiply this equation by 4 to give us 12 electrons, then multiply this equation by 3 to get 12 electrons, like a simultaneous equation. So when you do that, when you multiply the first equation by 4, you'll be having what you see on the screen. Then the second equation also multiplied by 3, you'll be having this on the screen. So now we have 12 electrons. We have 12 electrons at both equations. So 12 electrons there, 12 electrons there. They can easily cancel out. So when they cancel out, you add up the remaining. So when the electron cancel out, then you can add up the reactant and the product to give you your overall equation. So you see this 4 aluminium and 6 oxide are the reactant, then 4 aluminium metal and 3 oxygen gas at the product side. So that will be our overall equation. Yeah, before we leave on this place, on this particular aspect, what are the environmental risks of this Hall Heroult process? Number one, it requires huge amount of electricity that must be running 24/7 and 365 days a year, because if you remove the source of the electricity, the aluminium metal can solidify with the alumina and then the whole thing will get spoiled. So you have to continually run it without breakage. So it can only happen in countries that have stable and steady electricity. So that's number one disadvantage of that process. The second disadvantage of the process is the process leads to the production of carbon dioxide, which is which is a greenhouse gas. If you remember that when the carbon anode reacts with oxygen that is formed at the anode, CO2 is produced. That CO2 is a greenhouse gas that can lead to global warming, a very dangerous environmental problem. Then another environmental risk is the impact on the landscape. It deals with removal of resources that are non renewable. So it affects the topography of the land. Apart from affecting the topography of the land, there's a depletion of natural resources. So you can see this land now, how the topography has changed and all that because of mining of bauxite. So this process have those disadvantages, and uh, that's all erode process. So we can consider some evaluation question in this place. Describe the all erode method for extraction of aluminium. It's very easy. It's what we have discussed in this video. Then state why the anode need to be replaced periodically. I have told you that is because at high temperature, you must put it there because it's a wide question, and carries mark. At high temperature, the reaction can only occur at high temperature. It doesn't occur at low temperature. At high temperature, the carbon anode will react with oxygen that is produced at the anode and get burnt away or depleted, if you like, as carbon 4 oxide. Then number 3, give 2 reasons why aluminium extraction is considered to be expensive. Number 1, because it requires huge electricity cost. Number 2, because you have to be replacing the carbon anode at regular interval, so it adds to the cost of production of aluminium. Then number 4 states why the detection of aluminium is friendly environmentally, why that of sodium is not friendly. This also is a why question, and the reason is because when you extract aluminium, oxygen is produced as the gas, but when you extract sodium from down cell, remember you get sodium from down cell. When you extract sodium from down cell, chlorine gas is liberated. So chlorine gas is toxic, while oxygen gas is not toxic. So that is why you say aluminium extraction is friendly environmentally, while sodium extraction is not. Number 5 says state 2 reasons why cryolite is used in aluminium extraction. We said to reduce the melting point and also to increase conductivity, and it also acts as a solvent. So that will be the end of